Right, good morning everyone. We are going to go through some refreshers for what these two things are. These are things that you should have from previous courses. I've put here revision, and I've been in America for 3 years, or coming up for 3 years. I didn't realise that revision is a British, well, it's proper English, it's English as I know. This just means studying, okay? We are going through a refresher of what these things are. The best way that we can go through and understand both free body diagrams and method of joints, I'm going to go through an example, and I'm going to do the example by hand and concurrently code it up, and you'll hopefully learn when we're doing the next part, which is the force method, and I'll do a video on that afterwards, why it's useful to code these things up, okay, and why it's useful to have to hand a piece of code that does all of the legwork for you. Not really the legwork, but the number crunching for you. So I'm going to put a problem up. I'll take a little bit of time drawing this nicely, and then hopefully we'll go through that, and this should start to click into place. Okay, so if we've got a truss frame structure which has 3 nodes, 1, 2, 3, 3 members, 1, 2, 3, and an applied force. Here I've drawn it with a built-in support and a roller support, and if I give you a question like this, then I would have put some text to explain what these things are. For a question like this, I'm asking two things. I'm asking what the internal forces are. So there are 3 internal forces. There's FAC, FCB, and FAB we're looking to determine, and they're going to be a function of just P in this case. So that's to solve this part of the question, we need to do a free body diagram, and then the method of joints will determine the forces in each of these members. And after that, I'm asking if P is equal to 150 kilonewtons, E, or the Young's modulus, is equal to 190 gigapascals, and the cross-sectional area is 100 millimeters squared. What is the change in length of this member, AB? So does this get smaller, does it get longer, and by how much? Okay, so I'm going to go through this problem, and we're going to do this one first. To solve a problem like this, the first step is doing a free body diagram. So we're going to do a bit of revision of what a free body diagram should be. So for a body with an applied force like this, then there are 3 equations we can use to determine equilibrium. So we've got the sum of forces in the x direction, and the sum of forces in the y direction, and the sum of moments has to be 0. So looking at this problem here, we've got a fixed support, which is going to give a reaction force both in the vertical and the horizontal direction, and we've also got a roller support, which is only going to give a vertical support. So the first step is to redraw the problem just using the external shape of the body. Redraw the problem, including external shape, any applied loading, and reactions. So looking at the problem here, we can see that the reactions we would have, and again these forces, these arrows, the way that I'm drawing them, they mean being applied at the node. We would have FAY, FAX, and I would have here FBY. Okay, so the first step is to redraw the problem, including just the external shape. What do I mean by including just the external shape? Well, it's less important for a problem like this, but say I had a more complex truss, which say looked like this. That's a terrible truss that I've just drawn, but if that was my truss problem that I'm drawing, I would then just take the external shape, and I would then solve for the forces on just this external body. Okay, because this problem's got no internal members, we don't need to actually do anything different here, but we're going to redraw the problem. I'm going to have just a nice equilateral triangle, got my applied force P, and I've got my reactions here. FAX, FYX, sorry, FAX, FAY, and FBY. And I'll draw on here as well a frame of reference. Okay, so we've got to draw our axes on here so we know which direction is which. So what we're looking to do with a free body diagram is to solve for these values as a function of P. So the first one that's going to help us determine that is looking for equilibrium in the x direction, because we can see there are only two forces that are aligned in the x direction. So for the sum of forces in the x direction must be equal to 0. So for this problem, P is positive x, FAX is positive x. So P plus FAX is equal to 0. It follows that FAX must equal minus P. And when I do these, I like to draw a little tick just to remind myself which ones of these I've got. We can use the second equilibrium equation. Let's do sum of forces in the y direction has to be equal to 0. So the sum of forces in the y direction, I've got positive FAY, positive FBY. So FAY plus FBY must be equal to 0. It follows that FAY is equal to minus FBY. Now this doesn't help us, it hasn't given us one of these, but it's given us a relationship between these two. So we're sort of halfway there. And the last equation that's going to help us is the sum of moments anywhere on this body has to be 0. So I'm going to choose to evaluate moments here at node A. So that was A. I'm going to say the sum of moments going clockwise at A is going to be equal to P multiplied by this moment arm here. So that's this distance is going to be my L. Okay, let's just zoom in here. This distance is L. This is an equilateral triangle, so this angle is 60, which means this angle is 30. So L is equal to, in fact, the one thing I haven't drawn on this problem I should have done actually. Let's say it's an equilateral triangle and all of the sides have got length L, okay? And that means that for this problem I would also have to say over here, L is equal to 10 meters, okay? So this first one up here, this first bit we're keeping everything just as variables. It's an equilateral triangle, so each of these sides will have length L. And that means that, let's not call that L, let's call this H. So from the geometry, I can see that H is equal to L multiplied by cosine 30. So the moments going clockwise are going to be equal to P, which is the applied force, multiplied by H. And then I'm going to have a moment from FBY. So neither of these forces can cause a movement here, but FBY can. So it will be minus FBY, because any force, any moment due to a positive FBY will give me a counterclockwise moment here, multiplied by L. And we said that H with L cos 30. Cosine 30 is root 3 on 2. That's not one that I had remembered, but I should have remembered. So we'll say that. And P multiplied by L multiplied by root 3 divided by 2 minus FBY multiplied by L. Well, the sum of the moments have to be equal to 0, which you've got here, so this has to be equal to 0. So it follows that the force, or the reaction, FBY is equal to P multiplied by root 3 divided by 2. Okay? Let me just check where I'm up to. I want to check I've got my screens ready for the next bit. Okay, yeah, we're good. So we've got now reaction FBY, which means that using this relationship we have here, so let me just tick FBY off, and then use the reaction here, FAY has to be equal to the negative reaction of this. So FAY is equal to minus P multiplied by root 3 on 2. So we have our three reactions. So that's the result of the free body diagram. Okay, so if we're solving this problem by hand, then we only need to do this once. And for a simple problem like this that's statically determinate, we don't need to do this more than once anyway. But I'm going to just show you how to do this symbolically using Python, because it's going to become more important to do this for later problems. So let's keep this code up here. I'm going to bring a Jupyter notebook up. There we go. So we are going to use SymPy, and I probably don't need to use NumPy in this actually. I think I can just get by with using SymPy. So we'll do imports SymPy as SP. You can't see that line, I know, that's because, there we go, import SymPy as SP. So the way that I'm going to do these is I keep my free body diagram as a subroutine in here. So I'm going to make a subroutine called FBD. Make a subroutine, make a function, we'll say. I shouldn't call it a subroutine, really. Make a function for the free body diagram. So I'm going to store my applied load as a dictionary. Okay, and a dictionary just means that I can then apply my load up here, and I'm going to say that this force here is then the applied load at Cx. Okay, so the applied load at Cx, because it's at C and it's in the X direction. So I'm going to say define FBD, and it's going to be a function of the applied load. And what it's going to produce is going to give us out the reactions, and I'm going to store these reactions as a dictionary as well. So I know I've got this object, which is applied load, that comes in, and this is going to be a dictionary where I can get different applied loads out of it. For this problem, I've only got one, but then this is going to be a dictionary, and the Cx entry of that is going to be equal to P. So I'm going to say this first equation, which we've got here, says that the reaction FAX is equal to minus P. And for us, this is equal to minus whatever force is being applied up here. Okay, so then reactions. And I need to make the AX reaction, which is this bit here, is equal to minus whatever the applied load was in Cx. Let's capitalize this. Let's keep this. Okay, just when I concatenate words into variable names, I like to keep them capitalized like this. So applied load. There we go. You can use both double or single quotes. I tend to mix and match them because I've got bad practice. Okay, but we can do that in Python. It means just the same thing. So, okay, that's good. Now that gives me the reaction at AX due to Cx, which is this equation here that I've got is literally just this equation I've put down. So I've got to do the same with the others now. So the next equation was FBY is equal to P times square root 3 on 2. I'll say reactions, and I'm going to do BY is equal to applied load Cx multiplied by, and I'm going to use the SymPy version of square roots. Okay, so I'm using SymPy.square root 3 multiplied by 2. Let's just make this window slightly wider. And then I actually know that reactions for this problem, AY, is just equal to the minus of this. And then what it needs to return, reactions. Now, I'm coding this up as a subfunction, and I'm using dictionaries to store my variables in, or to store my object, using a dictionary object to store those different values in. If you're not that comfortable with Python, you might just prefer to store those as individual variables. It's up to you guys how you want to do this. If you're doing this in Excel, or if you do this in, say, MATLAB, I'm sure you'll do this differently. But I'm just showing you how I'm coding this up. Okay? Now, I'm not here to instruct you on every part of my methodology. I'm here to show you how I'm doing this, and we're here to learn the physics, and the computation just helps us to do things repeatedly. So I can test this now. So I've got this free body diagram. I'm going to, sorry, it's not returned, it's return. And you can tell there's an error because I know that keywords like def and return should be red. So when I get rid of the S, it gives me the proper highlighting. So as we did with symbols before, I'm going to make a symbol for the applied load. So the P is equal to sp.symbols, and I'm going to make it equal to just a capital P. And then I'm going to add this to the applied load, okay? So applied load is going to be a dictionary. So it's going to be with curly parentheses or curly brackets, and then the applied load at C in the X direction is going to be P, which is the symbol I've just created. I can then put this into my function, which is FBD. So I'm going to say reactions is equal to FBD, applied load. It doesn't like that because why doesn't it like that? Oh, it's because you can't start a dictionary like this. It needs to be equal to a dictionary like that. That's why. Okay, the error was here. Let me just undo that. Where I've run this, it says that this line 13 is invalid syntax, and if I go to line, oh, it's, yeah, okay. So if I go here, it shows me the line that was the issue. If I had a pre-existing dictionary, I could have added these with square brackets. But what I'm doing here is I'm saying this applied load is a dictionary, and we're going to initialize it with these values. So I run that, and we've got things, which is good. Let's just print out reactions and see what that looks like. Okay, so that gives me the reactions to my problem. Let's just check everything is what we expect. AX is equal to minus P, which is what we have up here. BY is equal to square root 3P on 2. Yep, that's right here, and the other one is just equal to the minus of that, which is correct. I'll just grab my camera, which has just fallen down. Excellent. Okay, you guys don't need to know all the ins and outs of how I record and everything, but I will say that to make sure that when I'm recording, the camera doesn't vibrate. So when I'm writing, if I was using my webcam, then the camera would vibrate, and that gets very annoying. I've got this set up on a tripod with a long sort of with a flexible arm holding it at a suitable place to record everything and to get a nice background. It means my setup is a little precarious. So I'm impressed that's the first time that's fallen down during the middle of a lecture, but that's what happened. That's why we're here. Let's just go back to where I got to. I'll try and re-get my train of thought. So I've got the correct reactions out. I just want to show you why I've chosen to use SymPy up here rather than NumPy. So if I go to these reactions and I change these to NumPy up here, use the NumPy square roots. Oh, it doesn't like them because I haven't imported NumPy. So I'll do imports. If I run these, I get the reactions out, but I get these out as decimals, and I just don't want them as decimals. Okay, I'd rather have them as surds. Okay, let's keep these as surds, then we get the reactions out as we expected to find them. So I've done the reactions, that's good. I'm going to park the Python for the moment, and we're going to go back to just looking at how we do the next step, which is doing the free body diagram. So we've got all of our reactions now. Free body diagram is done, and hopefully you guys can see how we can do this for more complex methods. And I'll sort of not rush through, but when I do more complex methods, I'll do the free body diagram and I'll do the method of joints spelled out explicitly, but I'll probably not put quite as much detail into my explanation as I go through them, because this should be revision, which might be a new word for you guys. So we've done that. The next step, if we're just looking to determine the forces, we need to do a method of joints. So let's look at the method of joints. So the method of joints is our means through which we can determine the internal forces on a statically determinate structure for which all of the external forces, including the reactions, are known. And what we assume that when we're doing a free body diagram, we assume that any structural deformations due to those applied loads are small. And by small, we mean that they're small when compared to the dimensions of the overall structure. And what that means is that if one of these members deforms, the actual angles and the orientations of these members with respect to each other doesn't change. Why is that important? Well, it's important because when we go through the method of joints, what you'll see and what you hopefully remember is that it's just a big geometric problem. We're looking to work out, there's a lot of trigonometry, we're trying to remember the cosines and sines of different angles, and if the structure deforms, those angles are going to change, but we're assuming those angle changes are very, very small when compared to the overall dimension of the problem. If we weren't able to make this assumption, it would make it a non-linear problem to solve, and that becomes much more complicated to go through. Okay, so we assume small deformations. I didn't mean that to be a question. We do assume small deformations. So I'm going to copy the problem again. Problem's coming down here. And we're going to do the method of joints. So the way that we do the method of joints is we pick a joint at which we can determine the forces due to nodal equilibrium. We've only got two equations for each node, which is that at each node, the sum of forces in the x direction and the sum of forces in the y direction have to be equal to 0. So we want to find a node for which that gives us a problem we can solve. So the things that we're trying to determine are these internal forces, and I'm going to use the sign convention that I'm assuming all of these are in tension. So these internal forces, I've got FCB, FAB, and FAC, and I'm assuming now that tension is positive. So what that means is I can pick one of these. I can see just from looking at the problem I could either solve C or B easily. Actually, I could pick any of these and I'd be able to solve all of them due to nodal equilibrium. It's just going to be easiest to start at C. So we pick a joint and we then redraw it. So I'm going to say pick node B. So I redraw the node, and then we redraw all of the forces that are present on this node. So, and I'm just going to use different colors to try and make it clear. I've got FCB, FAB, and I've got the reaction on here, FBY. So the blue ones are unknowns. This is a known thing that we've got. So if we can get FCB and FAB as a function of this, then we're good, then we know them. Now, if you'd gone through the problem and you'd been given a numerical value for this, you'd know this. But we already know that FBY is equal to P multiplied by the square root of 3 on 2, which means we can determine this force for any loading at C. So we've got this, and we're just going to keep it as FBY for the moment. The angle in here is 60 degrees. So you might have heard before that we use the etymology, or you can, sorry, not use the etymology, you might have heard your instructor say we want to cut members. Now I don't like that, because we're not cutting anything. We're not destroying the structure to do it. We are picking a node and we're viewing it in isolation with the forces that surround it. Okay, so those sort of, I just don't like the terminology of saying we're going to cut this and then look at it. It's up to you if you want to use it. If that helps you visualize it, that's fine. But it's not correct, and that's why I don't like it. We all know that I'm stubborn and like to be correct, though sometimes I'm not. So we've got this one here. I'm going to draw my axes on again. And I've got two equations that help me determine the equilibrium, which is the sum of forces in the x direction is equal to sum of forces in the y direction, has to be equal to 0. So it's going to be easiest to do the y direction first, because FAB and FCB have both got components going horizontally, whereas only FCB has got a component going vertically. So I'm going to say sum of forces in the y direction has to be equal to 0. So that is FBY plus the vertical component of FCB. So that's FCB multiplied by sine 60 is equal to 0. It follows that FCB is equal to minus FBY sine 60, I think, is root 3 on 2. Let me just check that. Again, there's all these things that you have to sort of remember when you're a student, but you can just look up in real life. Yeah, sine 60 is root 3 on 2. So this becomes FCB is equal to minus 2 FBY divided by root 3. And then I would go up here and I'd say, bingo, I've got that one. That's good. So I've got that one. The next equation I want to get to help me, I can use the sum of forces in the x direction. That's going to give me the horizontal component, sorry, the horizontal force here, which is FAY. So the sum of forces in the x direction has to also be equal to 0. So both of these forces are negative. Okay, so FAB is a negative x force, and the horizontal component of FCB is also going to be negative. So rather than writing these as minus FAB minus FCB cosine 60, I'm just going to write them added together. Okay, so FAB plus FCB cosine 60 is equal to 0. I think cosine 60 is a half. It is. So it follows that FCB is equal to 2. Just check, sorry, here. So FCB equal to FAB divided by a half, which is 2, so it's 2 FAB, which for us is equal to 4. Sorry, that is correct, but that's not the one I'm solving for. No wonder this didn't make sense to me. I want to solve for FAB, not FCB. So let's rewrite this. Let's just say We've already got FCB here. FBB is equal to minus a half FCB. FAB is equal to F BY divided by root 3. So I've now got these two forces, which means I have the two forces in this member. We zoom in, see that? Yeah, this member and this member. So the only member that's left to get is this one. Okay, and we can solve either by using up here, or I can solve by using down here. Now, if I solve it up here, then it means that my force in FAC is going to be a function of P directly. Whereas if I go down here, then I can solve for FAC as a function of FAY and FAC. Now, these I've already got defined as P anyway, but just the way that I like to solve it is I like to solve my internal forces just using the reactions. That's just the methodology I've chosen to do. So I'm going to now choose node A, and you'll find that if you choose node C, you'll get the exact same answer. Now, even though FAB is an internal force, I've written it in blue just because written it in green, just because we already know the value. Okay, so this is the only thing that we don't know. It's going to be easiest to solve FA. We could solve it in terms of the horizontal equilibrium, F, which is the sum of forces in X, has to be equal to 0. But it's going to be easiest to solve this using the vertical forces have to be equal to 0. So with this angle being 60, I can see that for my XY being these directions, the sum of forces in the Y direction has to be equal to 0. So it follows that FAY plus FAB sine 60 is equal to 0. FAB is equal to minus FAY multiplied by 2 on root 3. Okay, so I've got my FAB, sorry, have I messed up my numbers there? Yeah, I have, sorry, that's not FAB, that's FAC. That's my, it's because I've called the nodes slightly different things to when I solved this problem previously. That's my fault there. Let's call this FAC. Which means this and this should have been C's. There we go. Okay, so again, I leave these mistakes in because they help you guys learn, I hope. Let's just sort the focus out on this camera. There we go. I don't necessarily think I need to be in focus, but probably do better with a slight blur. But it's weird and jarring seeing myself. So whilst I'm rambling, let's stop doing that. I've got my 3 forces now, which are a function of my applied load. So I've now got, let's just check, do these look right to me? Yeah, these look right to me. I've got 3 forces, which means I've now got those. I can now go back to Python. I can write a subroutine for my method of joints. So let's go up here. And I'm going to make it a function of the reactions. I'm also going to say we could put the applied load in, but I'm going to say we don't have to supply the applied load. And this would be that if you decided to solve for node C as a function, if you decided to solve at node C, you would have had FAB directly as a function of P, okay, which for us would have been the applied load CX. So you would have to then input this here, but I'm going to put that there, and if you need to solve and you need to include that equation, you can put that in here, okay? But I've just set this as an empty default list going in. So we're not actually going to use this, but I'm just putting it here as a placeholder if you guys need to use it. So I now need to supply these three equations. And because I've just got everything is just a function of the reactions, I can solve these in any order. With more complicated structures, we'll find that later internal forces will be a function of other internal forces, and there's an order in which you have to solve them, but for this one, we're fine. So the first thing I need to do is put a internal forces is equal to an empty dictionary, and we're going to start populating this using the designation AB, AC, and BC, for example. So that's my internal forces, I'm going to call that. So internal forces, the first one I'm going to solve is this one up here. Internal forces, that is CB, is equal to minus 2 multiplied by its FBY, so that's the reaction BY. There we go, divided by square root 3. Let's just make the screen slightly wider so everything fits in. And then I'm going to do the second one. And now I'm going to do this one up here. Internal forces at AB is equal to the reaction FBY divided by the square root of 3. And then internal forces AC is equal to minus 2 times reactions AY divided by sin pi square root 3. And what I'm going to return from this function is the internal forces. So I've got those. We've now written this method of joints. Let's move this off. I'm going to try actually using this. So I'm going to say the reactions. So determine the internal forces due to the applied load. So I'm now going to put internal forces is equal to MOJ reactions, where reactions was determined up here. So we've determined the reactions and we've printed those out already. It's these values down here. MOJ reactions. Does this run? Doesn't run because there's a problem in here. It's got a problem. Key error CB. Internal forces CB is equal to. Why doesn't it like that? Oh, that's why. So what this is saying here, this is saying it knows internal forces as a dictionary, and it's saying what I thought I'd written here was make the CB key equal to this value, but I actually put here take that value and subtract this. I put a minus symbol in and not an equals, so let's just change that. This will now run. What doesn't it like now? Key error BY. So it doesn't have, that's okay, yeah, that's because I had these as uppercase up here. So down here it says key error BY, and what it's saying here, so BY occurs here, and it's because I've not been consistent with uppercase and lowercase. So let's do these like this. I'm going to keep the internal forces as lowercase though. There we go. So run all of those. I can now print internal forces. Okay, so that's telling me that member CB, which is the horizontal one, has a force of minus P, which means it is, that doesn't seem correct to me. Because I would expect that one to be in tension, so something isn't right here. So remember CB, just bear with me 1 second, I'm going to just take this off screen and just check what I've done incorrectly. No, forces were fine. I was being stupid. It's because I've just drawn this problem from memory. I've called these A, B, and C. And when I did this in the notes previously, I called it A, B, and C. So that's just my own doing things freehand, not trying to follow a solution. That's my problem. Okay, so we've now done this problem. We've printed out the reactions and the internal forces. We can print these out a little bit nicer than this, and I'll just show you a quick method. So we can iterate over the dictionary using the key and the value. So the key is the CB, for example, and the value is then the bit that we get out. So let's print them out nicely. So I'll say for key and value in reactions.items. So that means we're iterating over reaction.items. We'll say print. And this is what the value of putting these in dictionaries are, is that you can do this. So we'll do print, and we'll make this an F string. We'll say the reaction at node key, which is going to then tell me whether it says AX, AY, or BY. And then I'll do is value. There we go. So now I get this nice printing out. The reaction at node AX is minus P, which makes sense because that's this force here, which is the only bit that can react P here. The reaction at node BY is square root P on 2, and that makes sense. It's got to be in this direction because this is pulling the whole structure, causing it to go clockwise. This has got to push it counterclockwise. It's got to be positive. And then for vertical equilibrium, AY has to be negative, which is what we've got. I'm then going to just put a new line in. Make sure that's outside of the loop, otherwise it'll print a new line between everything. And I'm just going to copy this and replace this internal forces. So we'll say and we'll swap the bit that said reactions for the internal forces. And we'll say the internal force in member. There we go. So we now get these printed out. So the internal force in member CB, which is this one here, is minus P, which means this one is under compression, which makes sense because it's therefore the force is going in the opposite direction. The internal force in member AB is P on 2, and then the internal force in member A is minus P. So that's gone through free body diagram, method of joints. If we were given a value for each of these, for example, we could, let's just see if we can do this way, see if we can just set P is equal to 150E3. No, it doesn't. Let's go up here. I could do this just before I get here. Let's see if I can substitute that there. No, it doesn't do that. Oh, it's because I've done it up here. Okay, so if there's two ways there's many different ways we could get numerical values out, but because I called the applied load P here, I could just say P is equal to 150 newtons, and I would then get all of my values out as numbers here then instead. Okay, there's other smarter ways we can do this. I'm not going to go through these right now. Let's leave this where we are because this video is kind of long. This is an introduction to, or a reminder of how we do a free body diagram and how we do the method of joints. And here, hopefully, I've just shown you that if we do some coding, we enable things to, we can do things a little bit smarter. So, for example, if we'd done this problem, then you found, bummer, I've put the P going in the wrong direction. I would just go over here. I'd say my applied load. Okay, my applied load is equal to minus P instead. And if this was equal to minus P, so P was going in the other direction and we were pushing on it, I would expect this one to be in compression, this one to be in tension, and the bottom one I'd still expect to be in tension. So let's just check what we get out of those. Yeah, so I've got the internal force in member CB, which is this one, is now in tension. The internal force in member AB, which is the bottom one, is now in it will be in compression because this one's free to move. This one is fixed, so that's correct. And the internal force in member AC, which is up this way, is in tension. Okay, and that has to be the case because this one is in compression. Okay, so that's how we go through this problem here. Okay, so we've gone through that and just check that all the other forces sort of make sense. If we'd reversed it, this would then be positive. If we'd reverse this, this would then be negative. So we've got By is negative, and that makes sense. And then for equilibrium, this would have to be pulling down, okay, which is what turns this into a tension force. Okay, that's my buzzer on the door, so I'm gonna ignore that because I don't think it's for me. So no, I'm gonna go pause it. I think I'm just gonna go check what that is. Hello? Cool, come on in. Wasn't for me. My neighbour gets about 17 packages a day. I think unless those things are being destroyed, there's some thermodynamics laws that have been broken by the amount of stuff that's entering her apartment. Enough of that. So we've gone through this problem. Let's just have a little think about how we can make some more sense of these. So this next bit is completely extra, just what I want to help you with. Let's see if we can get the sign. And I don't know if I can do this actually, because at the moment we've got these outer symbol objects. Some of them are negative and some of them are positive. So let's see, because what I would like to see, I'd like to be able to see brackets under here, compression or tension. Now with symbols, I'm not sure if they have a sign or if there's a sympi.sign. So let's have a look. Let's do help sp.sign. Okay, so there is a sympi.sign. I just wanted to see if this worked. So let's do sp.sign p. No, that doesn't like that. I am going to do a bit of Googling and just see if I can find a sign function that we can use with SymP. Because I could just substitute the value of I could substitute a value in there and see if it's positive or negative, but I'd like to see if we can get that. Okay, so I've figured out a way to do this, a bit of a hacky way, but we'll show you guys. So down here, as we go through this, so the value that's being printed out for each of these is, let's run this again. I've got P minus P on 2 and P, and that's assuming a force of P. Now, SymPy doesn't know whether P is a number, it's an object, it's a symbol, and it doesn't quite know how to evaluate that. So there might be a smarter way of doing this, and if anyone wants to show me, that would be great. But what we're going to do is we're going to check whether tension or compression. So what I'm going to do is I'm going to substitute a value of 1 into that P and then check whether it's greater than or less than 0. So if P is greater, if value, which is the actual force that's present in that member, dot substitute, and I'm going to substitute P for 1. It's greater than 0. We'll say sense is compression, else sense, sorry I had that wrong, didn't I? It's positive, it's tension. And now what I can do here, there we go. So this is enabling me to say that the internal force in member CB is positive P, which is tension. Internal force in member AB is minus P on 2, which is compression. The internal force in AC is P, which is in tension. This has still got my negative P up here, so let's just get rid of this. This is the problem that we actually assigned at the very start of this. So it says that the internal force in AB is in tension, and then the internal force, that still doesn't make sense because one of these should not be, it shouldn't be. Member AC should be in tension. There's something wrong in here, I think. Let me just go back and check my equations. AY, that's Y. There's an error in my mistake. You guys might have gone through this. This AC isn't equal to this equation. This should be reactions AY. If I run this, I get the correct senses here, which actually meant these were slightly incorrect earlier. Okay, I keep these mistakes in because they show you how I recognize I've made mistakes through doing a little bit of sense checking and how I then correct for them. So I'm going to go through this, edit out the bit where my camera fell over, and hopefully that's given you guys a better refresher on how to do a free body diagram, what the method of joints is, and ways of coding this up so you can quickly change inputs to problems. And that's going to be really, really useful when we go on to do the force method, and I'm going to record a video on that now. Okay, so we're going to do the exact same problem, but instead of having a roller here, it's going to have two built-in joints. And we'll do the force method. We'll find that it's actually very, very simple for this problem because of the structure, and then we'll try and look at why that's more complicated for other examples and why we're going to start doing this work energy stuff. Okay, so thanks for tuning in. Remember, like and subscribe. It hurts me to say that, but I would like it if you did. And I will see you all in the revision a little bit later, and I'm sure none of you will have watched this because this probably isn't going to be ready until about the start of the thing. Sorry for the lectures being slightly late this week. I was stuck digging out a lot of cars on my street yesterday to help folks out. So I'm sorry for that, guys. But I will see you all soon, and I'm going to record another video shortly. Cheers.